Tracking a simple sine or cosine wave on a flat one-dimensional number line only captures a shadow of its true movement. The value bounces up and down, but it misses the complete geometry of the oscillation. To isolate and decode the overlapping frequencies hidden inside these waves, engineers required a mathematical upgrade. That upgrade is the foundation of modern medical imaging. The invention of the MRI relies on translating human tissue signals into this expanded space. All communications, GPS navigation, and Wi-Fi also depend on this same math to decode faint, complex signals beamed from space. Mastering the Fourier transform requires moving past the standard one-dimensional number line and entering a second, hidden dimension. By upgrading our math to include this vertical axis, complicated wave equations collapse into elegant, highly visual geometry that computers can solve. We start with an algebraic roadblock, the equation x squared plus 1 equals 0. If you move the 1 to the other side, you get x squared equals negative 1. No real number multiplied by itself can yield a negative result. To bypass this rule, mathematicians defined a new term, I, the imaginary unit. It is strictly the square root of minus 1. Rather than treating I as a fake concept, look at its geometry. Multiplying a number by I acts as a 90-degree counterclockwise rotation, lifting the value off the horizontal real number line and into vertical space. This creates a predictable cycle. I to the first power is I. Multiply by I again, and it rotates another 90 degrees to negative 1. Multiply again to get negative I, and a fourth time to return to positive 1. 4 rotations trace a complete circle. We map any point on this new 2D grid using a single expression called a complex number. The general form is z equals a plus bi. The letter a is the real part, written algebraically as re of z. It measures how far left or right the point sits on the horizontal axis. The letter b is the imaginary coefficient, written as m of z. The imaginary part is the multiplier b. The symbol I simply tells us to measure this distance vertically. An imaginary number is spatially real. The expression z packages a two-dimensional coordinate into one single mathematically manageable object. Mapping a point by moving right and then up works for static algebra, but for moving waves, it is more efficient to define our point by aiming an arrow directly at it from the center. This right triangle diagram shows how we measure the absolute length of that arrow, which we call the magnitude. Denoted by the absolute value bars around z, we calculate it using the Pythagorean theorem. Once we have the length, we specify the direction using the angle theta, measured upward from the horizontal real axis. In complex mathematics, this specific angle is called the argument, written as arg of z. When applied to physical signals, this angle tracks the exact phase of the wave. We also have an operation to instantly mirror any coordinate across the real axis. It is called the complex conjugate, written as z with a superscript star. By flipping the sign of the imaginary coefficient from plus 4i to minus 4i, the coordinate reflects downward. The geometric result of this conjugate is that it reverses the direction of the angle. This mirroring allows physicists to cancel out imaginary parts to extract real-world measurements. By switching to this polar format, the magnitude measures the wave's amplitude, and the argument specifies its days. This alignment between geometry and physics is formalized by one central equation, Euler's formula. E to the power of I theta equals cosine theta plus I sine theta. On a unit circle with a radius of 1, the right side of the equation tracks the physical location of the vector. Cosine theta maps the horizontal position, while I sine theta maps the vertical position. The left side, e to the I theta, takes both of those separate trigonometric functions and packs them into a single exponential expression. We turn this static geometry into motion by replacing the fixed angle theta with omega t, where t is time and omega is the angular frequency. The expression e to the I omega t is known as a phasor. Instead of a wave that bounces up and down on a graph, the phasor spins continuously around the complex plane. Before the clock starts ticking, the arrow has an initial starting angle. We denote this starting position with the Greek letter phi, which represents the wave's phase. Fourier analysis uses this format because managing one rotating vector is algebraically cleaner than calculating the derivatives and integrals of separate sine and cosine functions. By using phasors, dense trigonometric algebra becomes basic rotational geometry. The mathematical machinery required for the Fourier transform is now assembled. We can now construct the mathematical tool for continuous signals, the complex Fourier transform. Capital X of f equals the integral from negative to positive infinity of lowercase x of t times e to the negative I 2 pi ft dt. Lowercase x of t represents the raw input signal in the time domain. It is the chaotic, real-world data we are testing. Next to it is the complex exponential, e to the negative I 2 pi ft. 2 pi f is the angular frequency, omega. This is our spinning analysis phasor, sweeping through different speeds to test the signal. The integral sign and the dt dictate that we continuously multiply the raw signal against this spinning phasor and sum up the total area over time. As the equation tests a random rotation speed, the peaks and valleys of the multiplied signal usually cancel each other out, leaving a sum of 0. When the speed of the testing phasor exactly matches a hidden frequency, resonance occurs. The vectors align, producing a massive structural spike in the output. That output, capital X of f, is a complex number. It identifies which frequency was found, storing its strength as the magnitude and its alignment as the phase. This single equation executes a comprehensive frequency sweep, providing a complete frequency profile in one pass, without separate tests for sine and cosine. While the continuous integral works in calculus, computer processors cannot calculate infinite continuous functions. They require specific, sampled data points. To accommodate digital hardware, the continuous formula is adapted into the discrete Fourier transform. Capital X of k equals the sum from n equals 0 to n minus 1 of x of n times e to the negative I 2 pi kn over n. The continuous signal x of t becomes x of n, representing our individual data samples. The continuous frequency f becomes k, mapping into discrete, separated frequency bends. The calculus integral is replaced by the sigma symbol. It acts as a standard programming loop, iterating over and adding up exactly capital N total data points. Calculating this discrete sum point by point requires heavy processing power. The fast Fourier transform, or FFT, is the optimized algorithm that solves this exact equation using a fraction of the original calculations. This optimized algorithm is what runs inside the microchips of Wi-Fi routers, GPS receivers, and the processing units of MRI scanners. By expanding arithmetic to include the imaginary unit, mathematicians proved that one-dimensional waves are shadows of two-dimensional rotating vectors. This geometry provides the precise coordinate system required for the high-speed transmission and reconstruction of digital data.